Alright, so 17 here. Anybody got an idea of how to answer this question?
I have an idea, Mr. McCoy.
Alright, Amik, what do you got?
I have 3 heat of reaction.
Yes, heat of reaction. Very good. So, on a potential energy diagram, here's your reactants, here's your products. If your products have, let's say, 10 kilojoules of heat, and your reactants, let's say, have 40, to find the delta H, it's this segment here. The delta H is between your reactants and products. On your quiz tomorrow, you'll have to know this. So the value of it is actually going to be negative 30 because it's 10 minus 40. It's always products minus reactants. You don't have to memorize that, though. I don't believe you have to, because this is exothermic. If you understand this is exothermic, that has to be negative. We learned that a long time ago. Negative delta H means release energy. This releases it. That's why products are lower than the reactant. So that's heat of reaction number 3. Good. All right, number 18 is next. Here we go. Yeah, so here's what I'll do. I'll just kind of scroll up. It says, for a given chemical reaction, the addition of a catalyst provides a different reaction pathway, and here's your answers. So does the catalyst decrease reaction rate, have a higher activation energy? Decrease the reaction rate, have a lower activation energy? Increase reaction rate, have a higher activation energy? Or increase the reaction and has a lower activation energy? Megan, what do you think? 4. Yes, very good. We learned that from the demo. We learned that just from taking notes, talking about it, and explaining with the diagram. It lowers that bump. Corey said it yesterday. It lowers that peak. That's what the catalyst does. Lowers activation energy and increases. You could, I think everybody here probably crossed off 2 and 1 and 2 automatically, because catalysts increase the rate, right? Okay, one more. I'm going to have to zoom out for this one. 42, I believe. So I'll have to read it to you. Oops, wrong way. Some of you probably have a hard time seeing this. So basically what this is saying, if you can't read it, is there's a student who reacts 1 gram of zinc with 10 milliliters of hydrochloric acid. That's the same reaction I did when I put the, I had someone hold the cork. I poured the acid in, I said quick cork it, and I bubbled it through the soapy water and lit it on fire. That demo was the exact same reaction, zinc and hydrochloric acid. So it says the table below shows information about the variables in the 5 experiments. So I can zoom in a little bit on the chart. So here's your chart. Okay, you got experiment 1, 2, 3, 4, 5. You got lumps and powder, lumps, powder. 0.1, 0.1, 0.1, 1 and 1, and then 270, 290, 290, 280. So you got temperature, concentration, zinc, and then experiment 1, 2, 3, 4, 5. Here's the question. Which 2 experiments can be used to investigate the effect of the concentration of the HCl on the reaction rate? So which 2 experiments, 1 through 5, which 2, all right, and here, I know it's hard for you to see, you got 1, 3, 1, 5, 4, 2, and 4, 3, but I guess if I leave it like that, you can kind of see it probably. Which 2 reactions or experiments can you use to investigate the effect of the concentration of HCl on the reaction rate? Stay with it.
4.
3 and 4, so choice 4.
Yeah.
These 2.
Yeah.
You are correct. Why?
Because the temperature is the same and they're both lumps. The only thing that's different is the concentration of the HCl.
Good job. If you want to do a chemical reaction or any kind of experiment, and you want to see if one variable causes a change, one variable alone, you have to hold all other variables constant. So if we want to know only what change the concentration has on the reaction, what effect that has, we have to hold the zinc constant, so lumps is the same, and 290 hold temperature constant. So therefore, if experiment 3 you get a certain result, and then number 4, you get a different result. It has nothing to do with the zinc or the temperature. It has everything to do with the concentration of the HCl. You hold the other 2 constant, change 1. This morning I talked about little kids. I think in grade school you do this. I think you practice growing plants, and you see how water or sunlight affects it. Well, if you want to see how sunlight affects it or water affects it, you can't change both variables. You have to hold the water constant and then increase your sunlight, or hold the sunlight constant and then increase the water. You can't change both at the same time. So that's a similar concept. I think you guys are probably, you've been around, you've been in school long enough, you understand that. I hope you do that. You hold something constant, change the other one, and see how it affects it. Okay? See how that affects it. Questions on that? That's a really good Regents question, because I asked for questions and I kept talking, so I'll get back to that. It's a really good Regents question, because instead of just asking, how does concentration affect reaction rate, and then they give you choices, that's kind of straightforward and easy. They make it a little harder. You have to kind of interpret the graph or the chart. Questions? Okay, one more that has nothing to do with this, but it's a good review question. 14. I know we had a lot of problem with this when we did the bonding stuff, so I'm going to review this quite a bit. Hopefully it'll be on the test this year, and you guys can all smack it down.
4.
Close! Which one makes no sense whatsoever?
2. 1.
3.
2. How come 2? Well, 2 and 3, both of them,
Energy can't.
you can't produce energy, you can't destroy it. It is what it is, right? It just can be transferred. So, and in my head, I first read this, I just kind of laughed. I'm like, that's crazy. No kid's going to pick that. I hope not. Not anybody I teach. You can't destroy energy. So that doesn't make any sense. You can't produce it either. It can just be transferred. So it's either 1 or 4. And Ryan, it's okay. You picked the wrong one, but good try. So absorb. What does that mean? Energy is put into it. Energy is put into it. So if you want to, you have Cl2. So there's a Cl bonded to a Cl. You want to break that? You have to put something into it to break it. So you put energy in to break it. When you form bonds, they release their energy. So I'm going to say that a lot between now and your test and the end of June there. We'll go over this many, many times. By that time, you'll either memorize it or understand it, or hopefully both. All right, so that's that. Take out your notes. We left off with me playing with magnets, I believe.
I think you were going to, and then we got cut off.
Yeah, okay, maybe we got cut off. All right. So, Eden, I just got to keep a note here. The saturated lab there, you're still working on it?
Yes.
Caitlin, you too. Okay. This is not because you're bad people, or because you're bad students.
I'm sure.
It's not a thing like kids when they're little. Teachers do that. They write their name on the board. I don't know. I don't teach little kids, so I don't know. Okay.
Are you writing this down?
Yeah, write this down, please. I don't know exactly where we left off.
That's all
I'm
we
going to go writing this
That's
down.
about it.
It's the last thing I have.
All right, good. All right, so first of all, before I actually get into this, can someone tell me, when I say equilibrium, what are you guys supposed to think? Or what is the definition of equilibrium? Can anybody tell me? Me?
As one change is happening, as one physical change is happening, the opposite is happening at the same rate.
What if it's a chemical change?
Oh, then
Same thing.
yeah, same thing. That's it.
Chemical or physical change. If it's at equilibrium, you have 2 changes occurring at the same rate. So in this case, sorry Dan, I cut you off, but I saw him out of the corner of my eye. The forward and reverse are occurring simultaneously, literally at the same time. So at the same rate. So when something like this reaction is at equilibrium, these are coming together to make water at the exact same rate, same time. Water is breaking down into these 2. So, let's use an analogy. Who's it going to be? Megan. Megan's digging a hole. Megan has a shovel. She's outside, side of the school, just digging a hole. Corey, I use Corey a lot. Ben Ben has a shovel too. And he's standing next to the hole that Megan is digging. Every particle of dirt that Megan takes out of the hole, Ben puts it back in the hole. So literally every time she does this, Ben catches it and puts it back in the hole. So let's assume that that's happening, and every little particle that you get rid of, he's putting back in. Does anything really change? No. So it stays. Yesterday, what did I focus on? Constant. The size of the hole will stay constant. It won't get bigger or smaller because every time you take dirt out, you're putting dirt back in. So the analogy, and I can't take credit for thinking of that. It's a pretty good analogy. I got it from the video you're going to see. It starts off with that. It's okay. Either way, whatever helps you learn. So the concept of constant applies to equilibrium because if this is occurring at the same rate, the same speed, the same time, and this is occurring at the same speed, the same time, like the dirt, nothing ever changes. So what I mean is these come over here and they form two water particles at the exact same time as these two break apart and form oxygen. So nothing actually happens. Everything stays constant. So at equilibrium, a reaction really isn't doing a whole lot. It's staying constant. That's what I'm trying to show you. And that's what I'm hoping the magnets can help and the video will help, because those two concepts are more important than anything else we're going to do today, is understanding what it means to be at equilibrium. It means the rate of the forward equals the rate of the reverse. What does that mean? It means the amount of products and reactants stays constant. That's important to understand before we actually get into the video. Questions on that? So it's almost like, what's the point, right? What is the point of this? Because all reactions start out not at equilibrium. So when they reach it, then they don't really do much anymore. It's like the goal, to reach equilibrium. And if you look up here, this little balance beam type seesaw thing, the goal is to be balanced. The goal is to, I'm going to take this off, but I'll have to figure that out. The goal, this is, when we say equilibrium, like on the board, that's at equilibrium, I want you to start thinking of a seesaw as being balanced. That's equilibrium. You're going to learn something today called Le Chatelier's principle, where there's going to be a stress applied to the reaction, and it's going to be all screwed up. It's not going to be balanced anymore. Okay? So what happens is the reaction shifts some things around to make sure it goes back to being balanced. All right, and that's why I have some weights up here. So I'll show you kind of the concept, but in terms of a seesaw, imagine, everybody's on one side of the seesaw, so the other side is up in the air. The only way to balance it out is if some people from the one side go over to the other to get it to balance. That's the same thing in a chemical reaction. It does the same thing. So I'll mess with that later. That's not going to stay. Yeah. Let me show you the video. Actually, first I'll write down that word, Le Chatelier's principle, and then we will do some examples of it. And I forgot to give you your worksheet, so I'm going to do that while the video is playing. So it's called Le Chatelier's principle. I feel like I spelled that wrong.
Maybe you're saying it wrong.
Oh.
It better start with C-H. Okay.
I think you're just saying it wrong.
It's Le Chatelier, or some people say Le Chatelier, or Le Chatelier. That's how they say it.
Le Chatelier.
The chatty liar.
Okay, so let's make it dark in here, please.
Wait, you're talking about seesaws, so I was
Yep.
remembering from childhood way back.
Lights, please. Go
There
ahead.
was this little book, and it was about like this elephant. It sat on
Yeah.
a seesaw, and all the animals wanted to play on the seesaw too. And so they tried to balance it out, but they couldn't. And then they took like one little fly at the end to balance it out.
That's interesting.
Yeah.
So a seesaw with an elephant
And animals.
and animals and flies.
Yeah.
Okay.
Can we
All
tell
right.
ghost stories now?
So here's what I want you to do. You don't need to write anything down until I stop it and tell you to. So just watch. Really try and pay attention. Okay. Whatever you're thinking about, whatever you have to do later, whatever you're worried about or stressed about or whatever, try and clear your mind of that stuff and pay attention because this is a really good video. I say that sometimes a lot, but this one really is good as far as this specific topic. It explains it very well and adds good animation. So here we go.
In this lesson, you will learn about the Chatelier's principle, which explains what a system at equilibrium does in response to stresses. Let's return to our original example of you digging a hole and your friend refilling it simultaneously. If you start digging at a rate faster than refilling, the hole gets larger. In order to maintain a constant size of the hole, your friend must work harder to fill it faster. Following on the same idea, when a chemical system at equilibrium is stressed, the system works to restore equilibrium. This is the Chatelier's principle. The stresses are changes to the concentration of either the reactants or products, changes to the pressure, although this is only applicable to gaseous systems, changes to the temperature. Let's examine a hypothetical reversible reaction at equilibrium where reactant A reacts with reactant B to form product C and product D. If we added more A and B, the system becomes stressed and is no longer at equilibrium. To counteract the stress, the system forms more C and D in order to remove the excess A and B. The equilibrium, therefore, shifts to the right. If we added more C and D, the system becomes stressed and is also no longer at equilibrium. So to counteract stress, the system forms more A and B. Therefore, the equilibrium shifts to the left. What happens if we remove C and D as they are being produced, or if the concentration of C and D is decreased? Please pause the lesson to think about this and resume when you are done.
Okay, so if we remove C and D, don't answer. Think about what's going to happen based on what you just watched. Because right now, again, the seesaw analogy, we're like this. It's too heavy over here on your reactant side. So your products are too light, right? It's not balanced.
Make more products.
So you in your head should be thinking, all right, it's going to shift right or it's going to shift left. Think about that, and here we go.
The system is now stressed and no longer at equilibrium. To counteract the stress, more C and D are produced, so equilibrium shifts to the right. When concentration increases, equilibrium shifts to the opposite side of the reaction.
So we are going to be writing this down, but when you add something to this side, it has to shift this way to go back to being equilibrium. If I add something to this side, it has to shift this way to go back to being balanced. And I'll get this to balance better in a little bit. And I'll play with the weights, and it's just another visual for you. But that's important. The opposite is true. When you take something off, right? So I've seen students on the Regents use their pen or pencil, and I kind of have to tell them to stop because it's kind of cheating because they're sitting in a room and they're doing this with their pen. But it's not a bad thing. You could draw on a piece of paper in the margins of your test. This is balanced. That's not. That's not. So as long as you understand how a seesaw works, you can figure out, well, okay, well, how does it have to shift to go back to being balanced, right? So if I take something off this side, it's going to look just like that. It's going to be like this. Well, it's going to have to shift that direction to go back to being balanced, right? Think of it as weight. And hopefully this is going to help you understand how this principle works. So that was with concentration. The next one's with pressure. Pressure is harder to understand, so we'll see how you do.
When concentration decreases, equilibrium shifts to the same side of the reaction. Changes in pressure. The stress to a system at equilibrium is only applicable to gaseous systems. For this stress, we will examine another hypothetical reaction at equilibrium, where reactant A reacts with 2 moles of reactant B to form product C and product D. An increase in pressure means that there is a decrease in volume, so there is less space. Equilibrium will shift to the side of the reaction with fewer moles. In our example, an increase in pressure will cause equilibrium to shift to the right, since there are fewer moles. 2 moles compared to 3 moles on the left. A decrease in pressure means that there is an increase in volume, so there is more space. Equilibrium shifts to the side with more moles. So in our example, equilibrium shifts to the left. So an increase in pressure favors the side with fewer moles, and a decrease in pressure favors the side with more moles.
That's why it's difficult, okay? That's not easy to follow. It's not as easy as the seesaw analogy. That doesn't really work for this. So the way I tell kids usually is to try and memorize it. I just kind of give in to that it's very hard to understand if you, again, I always say this, if you take AP Chem or College Chem, you have to understand it more, and there's a little bit more time to spend on it. But Regents Chem, if you increase pressure, it goes to the fewer moles, and decrease pressure, it goes to the side with the greater number of moles. So we will go over that again. But again, the animations, the pictures, I think are pretty good here.
In our next lesson, you will learn about how a system works to restore equilibrium in response to changes in temperature. In summary,
We'll do that
the
tomorrow.
Chatelier's principle states that when a system at equilibrium is stressed, the system works to restore equilibrium.
Okay, write that down, please. In your notes, under Le Chatelier's principle. When a system at equilibrium is stressed, the system works to restore equilibrium. And I'm going to stop it now, and then we'll, I'm going to mess with this thing here. And then I'll explain that worksheet. You're not doing the whole thing.
Yeah. Are we going to use the reference tables for this worksheet?
Nope.
Oh, cool.
I don't think I moved it. Oh, it's-
That's pretty
We'll
good.
go with it. That's good. Okay, I'm going to turn this off. Lights please, and can you guys open those up again? So, here's the stress. Or let's talk about the homework first. So, go to this side here with the 2 charts. Okay, you're going to do this whole thing between now and Friday, but just do tomorrow. Just for tomorrow, you're not going to do 7, 8, and 9, 7, 8, 9, 10 on the top. Don't do that. Don't cross it off or anything, because you're going to do it tomorrow night. You're not going to learn. You're not going to learn about it yet. And then on the bottom, don't do 5, 6, 7, 8. Okay, so you can skip those for tonight. Flip it. The other side, don't do 7, 8, 9, 10. Again, those will be due Friday, but I want to teach you first. And the last column, K, where it says K on both sides, you could cross K off. You don't have to do K. That's an AP Chem thing. I'll explain it probably just briefly, but you do not need to know. All right, so let's see. Where are my directions here? I wrote myself a little script. So if you can, I want you to move your head, body, desk, so you can see what's going on here. All right, so we're at equilibrium, let's say. Let's say we have a reaction. Here's our reactants. Here's our products. It's at equilibrium. I'm going to add more reactants. I'm going to put 400 grams over here. There's 4 100 gram masses there. Okay, so now I stressed the system. I added too many reactants. It's not balanced. What does it do to shift? How does it shift? What happens? 200 go over here, right? Does that make sense to everybody? So if I take 200 and it shifts towards the, bless you, what's this called? Shifts towards the products, or towards the right. Okay? It may not be perfect. I know that, so don't take it to be perfect. But it's going to be fairly balanced now. In real life, the reaction would be. So when I think balance, I think equilibrium. So I'm shifting this to the product side. I just realized that this is not on the thing.
Don't drop it. We don't want to have.
Just temporarily.
We don't want to be.
When we
second
take
guessing.
notes, I'll take it off your desk. Thanks.
All
Alright, so, she's just nervous because, you know, Destiny. Anyways, now it's balanced, it's at equilibrium. So, now I'm going to do something else here. What am I going to do? I'm going to take 4 20-gram weights, put them on the product side, and I'm going to put 4 10, did I say 20-pound?
Yeah.
Man, I'm
No, you said
strong. I just
20
looked those
gram.
up in my, I did? I feel like I said pound.
No, you said.
You said.
Anyways,
Oh, you said gram.
4 10 grams. So I have
My
4
hearing is bad.
4 20 grams and 4 10 grams over on the product side with those 200s. Okay, so what's wrong with this? It's stressed out, so it has to shift. What happens?
You have to take two of each. 2 20 grams.
2 20 grams. Let's put those over here. So which way am I shifting now?
To the left.
To the left, towards reactants. I'll take 2 of the 10, 2 of the 20, and let's see if that's going to balance out.
Beautiful.
And once it stops doing that, it will balance out. Okay? So, again, if I add too much to the product side, it shifts towards the reactants. So, keep that in mind. When you add something to your reactants or products, it always shifts away from that. Okay? And the last thing, I'm probably taking things off, I'm going to take 120 off of the product side. Whoops. Okay. Now I removed a product. What happens? Tara, you with me? Okay. Eve, totally with me. What happens?
This side.
What?
Oh, it's stressed on that side.
It's right. So how does it shift?
Let's take one from this side.
Yeah. So what direction does it shift?
Left,
Right.
or left, your right.
Yeah, towards the. Let's say it's called products or reactants.
Oh, towards reactants.
Towards. Try again.
Product.
It tilted this way.
Right. So now how does it shift to go
Oh,
back to
yeah.
equilibrium? Right. So it has to shift towards products, and I'm going to take one of the 10s. Right?
No. Wait.
Try again.
One of the 10. Yeah, I thought I could do math for a second. So you take one of the 10s, shift it, and it'll be at equilibrium now. So the reason I'm doing this is to literally show you this is how reactions do it when you add or take something away. So let's think about this. I took that 20 off. How did that affect, listen carefully, how did that affect the concentration of the reactants? Don't answer out loud, just think. I took this 20 off of here, so it was like this. Now it shifted 110 gram over here. So what happened to the amount of reactants, which is the concentration of the reactants? Michelle. When I took this 20 off, it was tilted like this.
Right.
So then it shifted. I mean, I did it, but in real life, the reaction would do it on its own. It took 10 grams and shifted it over here. So what happened to the concentration of the reactants?
Kind of equaled out.
Did it go up or down? So do I have more reactants here or less than before? So before, this is what happened. Here, let me back up. So I had this here.
You had more over there.
I had this here. No, it was at equilibrium.
It was there.
It's at equilibrium. It's gonna balance out here in like 30 seconds. So it's gonna balance out. I took 20 grams off, so it's not at equilibrium anymore.
Right.
So 10 grams here shifted to the right towards the products, so it can go back to being balanced. What happened to the amount of reactants?
No.
Try again.
Went down.
The amount of reactants decreased.
Yes.
I took one from here and turned it into a product. So I took one from here, it doesn't have it anymore, so it decreased in concentration.
Right.
Does that make sense?
Yes.
Everybody else follow me there? Somewhat?
Well, we
I hope.
need.
Ish.
Okay, ish. All right, we're gonna do some more problems here on the board. So, write this down, please. Concentration changes, and then a little bullet. Increasing the concentration of reactants. Increasing the concentration of reactants causes the equilibrium to shift towards products. Ben, you with me?
Yeah.
Which makes sense. If you add more reactants, does it make sense to you people that you make more products?
Yeah.
That's exactly what happens. Okay? It's nothing you don't already know. Everybody knows that. Who takes chemistry? You add more reactants, you make more products. That makes sense. Okay? And then the opposite is true as well. If you decrease, well, this one doesn't make as much sense. I mean, this would be great. Because I always think of gas, and I put gas in my car. Put gas in my car, I can drive further because I have more gas, right? So that's a good thing. If I decrease the concentration of reactants, I wish this happened. If I decrease the concentration of reactants, it causes the equilibrium to shift towards reactants. Which means if it was gas and I decreased the amount of gas in my car, magically there would be more gas there as I used it. That would be pretty cool. But that doesn't happen.
It would be like a never-ending supply.
Never-ending supply. Some equilibrium reactions work that way. If you have enough products and reactants, they just keep replenishing
So
themselves.
it's like a big circle.
But eventually you would have to add more.
So it's like that recycle sign.
Sort of. Just right. That's why there's 2 arrows.
But in
You're
a
thinking, I
recycle
was
sign,
thinking.
there's 3.
Is
I
that?
know that.
Oh, it's still arrows.
Did you guys know there's an arrow in the FedEx sign?
No.
Yes.
I did not know that till yesterday.
What, in the
What?
X? What are you talking about?
There's an arrow in the FedEx. The symbol for FedEx, FedEx, it's their name and symbol. There's an arrow in it.
I didn't know.
Did you know that there's life in the coconut?
I'm glad that's recorded too. All right.
Learn something new every day.
This class.
All right. That was pretty funny. All right. Moving on here. N2 plus H2 yields NH3. Put a 2 here, put a 3 there. These are all gases. I'm going to use this as an example. We'll do at least 2 practice problems and then that'll be it. So here is your equilibrium reaction. So given the following is what it might say. Given the following, here's the question. If the concentration, some of you I know get lazy and you don't like writing the actual question down. You have to, otherwise you have no idea what the answer means. Okay? So write it down. If the concentration of H2 gas is increased, this is a very typical Regents question. If the concentration of H2 gas is increased, in what direction will the equilibrium shift? This is why I use the analogy of a seesaw, and I show you that in the video to help you understand how to answer these questions. So go ahead and start trying to figure that one out. While you're doing that, I'm going to write another question up here underneath it. If the concentration of H2 gas is decreased, if the concentration of H2 gas is decreased, in what direction will, whoops, nope, I got on autopilot there, I'm sorry. My fault. I want to ask a different question. Sorry. If the concentration of H2 gas is decreased, how is the concentration of NH3 gas affected? And by affected, I mean, does it increase, decrease, or remain the same? So go ahead, think of those 2 answers. Brad, for some reason I have you missing review book chapter 10. Would that have been the one in the book?
That's the one that I did in the book in there. That was the first one we did.
Ben, I got you missing some book work. I'm going through here to let you guys know because Friday's the deadline. And then Amit, that lab, half of that balancing equation lab.
Yes.
You know what I'm talking about, right?
Yes.
I need that by Friday.
Is that a sinker? The 10 gram weight there?
Oh my
I
gosh,
don't think
Brad.
so. It's just the weight for
It looks like a sinker.
And that's it. Everyone else,
Yeah, he
you're
has.
good to go. Alright, here we go. So I just wanted to do that quick while I was thinking of it. Here we go. First question. Who can tell me which way does it shift? Go ahead, Destiny.
Left?
It shifts to the left. Try again.
Oh.
Hey, do the seesaw. So this thing is a giant seesaw, this reaction. Where the heck am I putting my markers? So here's your seesaw. If we add more here, put a bunch here, what's going to happen to that seesaw? Yes. So now how does it shift to go back to being balanced?
Oh, see, I got you.
That's okay. That's why we're practicing. So it shifts
Right.
to the right. So everyone listen, please. This is how it looks initially. If you add hydrogen on this side, it's too heavy on the reactant side. So it shifts to the right to go back to being balanced. So it shifts towards the products. Okay? Shifts towards the products. So it's not about how it first tips, it's about how to get back to being balanced. Does that help a little bit? Now, next question. If we decrease H2, so now here, if we decrease H2, look up here, we take it off this side, I'm like this now, right? Because if I take these weights off, that's what happens. How do I make that balanced? It has to shift this way, so it has to take some of the weight and shift it to this side. So what does that do to the amount of the products? It decreases it. So it decreases. It decreases the amount of NH3 because it's shifting to the left in that question. Okay? So those are just a couple to help you get the idea. Oh, sorry, I forgot to put that back here. Can you even see the board?
So, do you have like
Yeah,
a
sorta.
YouTube channel with every single day?
Yeah.
Every single day.
Every day I record, yeah.
So after you're done working, whatever you